Far beyond what human eyes can see, the universe is glowing in hidden colors. NASA's SPHEREx is now scanning the entire sky in 102 infrared wavelengths, revealing faint galaxies, frozen water, cosmic dust, and structures that visible light leaves behind. This is not a different universe. It is the same one, seen more deeply than ever before. If this kind of calm cosmic journey belongs on the channel, please like the video, subscribe, and stay with the story. A first view of this hidden universe begins not with a single star or a single galaxy, but with the sky as a whole. SPHEREx moves through low Earth orbit and looks outward in every direction over time, building a survey that does not select a few special targets and ignore the rest. Its work is broad, even, and patient. It treats the sky as one connected field of light. From that field it gathers infrared radiation, a form of light with wavelengths longer than visible light, and it separates that light into 102 distinct bands. Human eyes do not see those bands directly, yet they are present across the sky, carried by dust, stars, galaxies, gas, and the faint combined glow of distant sources. In this wide beginning, the universe does not appear as darkness broken only by scattered points. It appears as a surface rich with hidden structure, where every direction contains information that ordinary sight leaves out. This is the central change that SPHEREx brings. A familiar sky map often records where objects are and how bright they seem in one broad range of light. SPHEREx records something more layered. It asks not only where light arrives from, but how that light is distributed across many narrow slices of wavelength. That distribution is called a spectrum, which is a measurement of light separated by color. In astronomy, a spectrum can show whether light is rising, falling, blocked, or enhanced at particular wavelengths. Even when the detail is not as fine as in a large observatory aimed at one object for many hours, the result still carries strong physical meaning across the whole sky, repeated again and again. That meaning accumulates into a new kind of map. In visible light, the sky can seem clean and simple in some directions and crowded in others. In infrared light, the balance changes. Cool material that is dim to the eye becomes easier to trace. Dust that blocks visible light can itself shine, or allow longer wavelengths to pass through more effectively. Regions that look empty can reveal broad veils, streams, and diffuse glows. Bright stars remain present, but they no longer dominate the scene in quite the same way. The sky becomes less like a sparse field of isolated lamps and more like a continuous record of matter and energy spread through space. The phrase 102 colors does not mean decorative color in the ordinary sense. It means 102 measured windows into physical reality, each one sensitive to a slightly different range of infrared light. Because SPHEREx surveys the entire sky, its map has a quality that narrow missions cannot fully provide. It places every source within a common framework. A feature in one constellation and a feature far away in another can be compared with the same instrument, the same observing method, and the same system of calibration. This uniformity matters. Astronomy often advances through deep study of small chosen regions, but a full sky survey adds a different strength. It shows patterns that only become visible when nothing important is left outside the frame. It reveals gradients, asymmetries, boundaries, and alignments that are hard to recognize when the sky's divided into isolated pieces. The whole sphere overhead becomes a single scientific surface. SPHEREx also turns time into part of this map. As the spacecraft continues its scanning pattern, it completes repeated all-sky coverage. The first complete survey is not the last word. Each pass adds depth, checks consistency, and sharpens the picture. Weak signals become more secure. Instrumental effects become easier to separate from real celestial structure. Changes in observing geometry can help fill gaps and strengthen confidence in the final data products. The result is not one frozen glance, but a carefully assembled record. During its primary mission, the all-sky map is built again and again, then merged into a more complete view. At this larger scale, the hidden universe is not hidden because it is rare. It is hidden because human vision covers only a small part of the electromagnetic spectrum, the full family of light. Visible light is only one narrow interval within that family. Infrared lies just beyond it, and much of the universe radiates strongly there. Warm dust, cool clouds, faint distant populations, and chemically rich materials all leave marks in infrared wavelengths. A mission that observes only a few colours can detect some of this. A mission that observes 102 colours across the whole sky can separate those contributions with far more clarity. It can tell when two regions that look similar in brightness are in fact different in composition or condition. It can also show when sources that appear different in ordinary images are linked by the same broad spectral behaviour. This wide survey has another quiet strength. It is public, systematic, and built to be used alongside other observatories. A full-sky infrared map in 102 bands becomes a reference layer for astronomy itself. Other telescopes can study smaller regions in finer detail, but SPHEREx provides context around them. It helps identify where unusual colours appear, where dust changes character across broad areas, where large populations gather, and where known catalogues remain incomplete. In that sense, the mission does not replace more focused astronomy. It steadies it. It gives researchers a common background against which many separate observations can be understood. Seen this way, the opening region of the SPHEREx story is not a place with a boundary. It is the entire celestial sphere, wrapped around Earth and sampled methodically in infrared light. Every direction becomes part of one survey. Every measured wavelength adds another thin layer of description. The sky that seems black between visible objects proves not to be empty. The bright objects themselves prove not to be simple points. Their light carries shape across wavelength, and that shape can be mapped over the whole heavens. SPHEREx begins with breadth before detail, with coverage before selection, and with colour before classification. In doing so, it changes the first act of observation. It makes the wide sky readable in a new language, one built from measured infrared colours spread across the full dome of space. Across the full sky, beneath the brighter pattern of named objects, a softer field of light remains. It does not gather attention in the way a bright star does. It does not form a sharp outline like a nearby cloud. It spreads, blends, and persists. This is the diffuse cosmic glow, a broad background of infrared light that reaches Earth from many directions at once. Some of it comes from material close at hand, and some of it comes from sources so distant and so numerous that their individual forms dissolve into one shared brightness. SPHEREx measures this glow across 102 infrared colours, and in doing so it studies not only separate objects, but the light that fills the spaces between them in a statistical and cumulative way. A diffuse background is light spread over the sky rather than concentrated into easily isolated points. In astronomy, this kind of glow matters because it contains information about countless sources that are too faint, too distant, or too crowded to be studied one by one. The light still arrives, it simply arrives blended together. When many generations of galaxies emit starlight, when dust absorbs part of that light and re-emits energy at longer wavelengths, and when all of those contributions overlap across immense stretches of space and time, the sky carries the result as a faint all-sky background. It is not uniform in every direction, and it is not featureless, but it is subtle. To detect and interpret it, a mission must measure the sky evenly and repeatedly, with careful control of instrumental noise and foreground contamination. This is one reason an all-sky infrared survey is so valuable. A diffuse glow cannot be understood well from a few isolated fields alone. It must be measured over very large areas so that real celestial patterns can be separated from local effects. SPHEREx is designed for this broad task. Its maps let astronomers compare one direction with another in the same wavelength bands, under the same observational system, until a coherent background picture begins to emerge. The mission does not search only for the brightest known objects. It also records the low-level light between them, and that low-level light becomes one of the mission's most revealing products. The phrase total light from galaxies refers to something simple in principle and difficult in practice. Over cosmic history, stars form inside galaxies and radiate energy. Some of that starlight travels freely through space. Some of it strikes dust grains inside galaxies, where it is absorbed and then re-emitted in infrared light. Some galaxies are bright and obvious, while others remain too faint for direct detection in ordinary imaging surveys. Yet all of them add to the sky's overall brightness. By measuring this accumulated glow, SPHEREx helps estimate how much light galaxies as a population have produced over time. This offers a different route to understanding cosmic history. Instead of starting with one catalogued object after another, it begins with the combined record of many objects together. The background is not a smooth sheet laid over the universe from outside. It is the sum of real astrophysical processes. It carries the imprint of star formation, dust heating, and the slow red shifting of light as the universe expands. Redshift means that light stretches to longer wavelengths while travelling through expanding space. Because of that stretching, radiation emitted long ago in shorter wavelengths can arrive today in the infrared. This is one reason the infrared sky contains such a deep historical record. Light that begins in distant galaxies does not preserve its original appearance unchanged. By the time it reaches a modern detector, it has been shifted, dimmed, and blended with other contributions. The background that results is faint, but it is rich in memory. SPHEREx is especially well suited to this work because it does not observe the sky in only a handful of broad filters. With 102 spectral bands, it can trace how the background changes with wavelength in a more continuous way. That matters because different physical sources leave different spectral shapes. Starlight that escapes directly into space does not have the same wavelength pattern as dust that has absorbed energy and warmed. Light from nearer populations does not have the same distribution as light that has travelled from much earlier cosmic epochs. The signals overlap, and they cannot always be separated cleanly. Yet the added spectral detail makes it easier to model what portion of the glow comes from which broad class of source. There is also a practical challenge in this measurement. Before the distant cosmic glow can be inferred, brighter foreground light must be recognized and accounted for. Dust within the solar system scatters and emits light. Material within the Milky Way also contributes broad infrared emission. Instrument detectors have their own thermal behavior and noise properties. None of these facts weakens the value of the diffuse background. Instead, they define the care needed to reveal it. An accurate map of faint cosmic light depends on calibration, repeated sky coverage, and comparison across wavelengths. The final measurement comes from patient subtraction and cross-checking rather than from a single direct image of a glowing cosmic wall. Even after these foregrounds are modelled, some uncertainty remains. Observations indicate that galaxies produce a large fraction of the diffuse extragalactic infrared and optical background, yet it remains uncertain whether every part of the measured glow can be fully explained by known populations with present models. This uncertainty is scientifically useful. A mismatch between integrated galaxy light and background measurements can point to incompleteness in catalogues, limitations in foreground removal, or missing details in the history of dust-obscured star formation. A full-sky mission does not erase these difficulties, but it reduces them by providing consistent measurements over a vast area and across many wavelengths. In this wide and gentle glow, the universe appears not as a collection of isolated beacons, but as a long accumulation of radiance. Countless stars burn, dust grains absorb and release energy, galaxies brighten and fade, and the record of that activity spreads across space until it becomes a background field. SPHEREx listens to that field in infrared colors fine enough to separate parts of its story and broad enough to cover the whole sky. The result is a map of collective light, where the faintest layers matter as much as the brightest points, and where the hidden universe begins to show itself not only through objects that stand out, but through the soft luminosity they leave behind together. Beyond the faint shared glow of accumulated light, a larger pattern emerges from the positions of galaxies themselves. They do not lie through space at random. Across the observable universe they gather into an immense arrangement of strands, knots, sheets, and open regions. Astronomers call this arrangement the cosmic web. The term describes the large-scale structure formed as matter responds to gravity over cosmic time. Galaxies collect along denser lanes, galaxy clusters grow at crowded intersections, and wide voids remain between them with far fewer galaxies than average. This pattern is not decorative. It is a direct record of how the universe changes from a nearly smooth early state into the structured cosmos seen today. At the largest scales, a single galaxy matters less than the population around it. What matters is where many galaxies sit relative to one another, how tightly they cluster, how far the strands extend, and how the emptier regions open between them. When enough galaxies are measured across enough sky, their distribution begins to reveal a hidden architecture. The web is not built from visible threads. It is built from positions, distances, and density contrasts. A density contrast is simply a difference between regions with more matter and regions with less. These differences start very small in the early universe. Gravity then strengthens them slowly, pulling matter towards slightly denser places and making emptier regions more empty over time. SPHEREx contributes to this picture through breadth and consistency. Its survey covers the full sky and collects spectra in 102 infrared bands, giving astronomers a way to estimate the distances of very large numbers of galaxies across a common observing system. A distance estimate from shifted spectral features is not always as precise as one obtained from a more focused instrument, observing a single object in detail, yet it is powerful when applied to hundreds of millions of galaxies over enormous areas. The value lies in scale. A map containing vast numbers of galaxies can show not only local groups and bright clusters, but also the longer continuity of the web across broad volumes of space. This matters because the cosmic web is a three-dimensional structure. A flat sky map alone can show where galaxies appear on the celestial sphere, but it cannot fully show how they are arranged through depth. Two galaxies may seem close together from Earth, and yet lie at very different distances. Spectral information helps separate that overlap. As light travels through expanding space, its wavelengths stretch. This redshift carries information about distance on cosmic scales. SPHEREx is built to measure this effect in a broad survey mode. By doing so, it helps turn a two-dimensional sky crowded with points into a volumetric map in which filaments, concentrations, and open regions become easier to distinguish. The web itself reflects the long action of gravity upon matter, both visible and dark. Dark matter is matter inferred from gravitational effects rather than directly seen in light. In the standard cosmological picture, dark matter provides much of the underlying scaffolding on which ordinary matter gathers. Gas falls into these gravitational wells, stars form inside galaxies, and galaxies settle into halos and larger systems. SPHEREx does not detect dark matter directly, yet the galaxy distribution it records traces the influence of that hidden mass. The visible web of galaxies follows a deeper gravitational framework that cannot be seen by eye. In this way, the map of galaxies becomes a map of unseen structure as well. Even the emptier parts of the web are informative. A void is not a complete absence of matter. It is a region with much lower density than average. These broad sparse spaces help define the shape of the denser lanes around them. In the cosmic web, emptiness is part of the structure. Large voids widen as matter flows outward from them toward denser boundaries. Their presence gives the web its cellular appearance on the larger scales. An all-sky survey is especially useful for this reason. It does not isolate only the crowded places that draw attention first. It also preserves the larger spatial context in which sparse and dense regions alternate across the sky. The infrared nature of the survey adds another advantage. Some galaxies lie behind dust-rich regions of the Milky Way, where visible light observations become more difficult. Infrared light can penetrate dusty foregrounds more effectively, allowing a more continuous sense of the sky. No survey sees perfectly through every obstacle, and no single mission removes every selection effect. But infrared coverage helps reduce a major source of incompleteness. This matters for large-scale structure because artificial gaps in a map can imitate or obscure real cosmological patterns. A smoother and more uniform sky census gives a truer picture of how galaxies actually occupy space. As this web is measured, subtle regularities appear within it. The clustering of galaxies is not entirely arbitrary at any scale. It preserves statistical traces of physical conditions in the early universe. Over time, those traces are altered by gravitational growth, galaxy formation, and cosmic expansion, yet they are not erased. A survey like SPHEREx therefore does more than chart where galaxies happen to be. It records how structure itself grows, how matter gathers across time, and how the present arrangement still carries memory of far earlier conditions. The cosmic web becomes both a present-day map and a historical record. What appears, then, is a universe whose broadest visible order is neither smooth nor chaotic. It is connected. Galaxies inhabit corridors of enhanced density. Clusters sit where those corridors meet, and emptier domains open between them like slow cavities in a rising structure. SPHEREx traces this arrangement across the sky, not by drawing literal lines, but by measuring the light and distance of immense galaxy populations in the infrared. From those measurements, the hidden geometry of the cosmos comes into view. The web is not seen all at once by ordinary sight, yet in a full-sky spectral survey it becomes legible as a real and coherent form, stretching across the depths of space with quiet continuity, far beyond the Milky Way and beyond the nearby web of recognizable galactic neighborhoods. The sky holds an immense population of remote galaxies whose light arrives from many different ages of cosmic history. Some are bright enough to stand apart as individual objects. Many more are faint, small, or distant enough that they do not draw immediate attention on their own. Yet their light still enters the survey. It still contributes to the measured sky. In this region of the SPHEREx story, the focus narrows from the broad geometry of where galaxies gather to the radiation those galaxies produce across time. The hidden universe here is a record of distant galaxy light, not only from the obvious sources that can be named one by one, but also from the vast population that can be studied most clearly in aggregate. A galaxy is a gravitationally bound system of stars, gas, dust, and dark matter. Its light comes from several processes acting together. Stars produce direct radiation from their hot outer layers. Gas within galaxies can glow when it is heated or energized by nearby stars or active central regions. Dust grains absorb part of the shorter wavelength light, and then release that energy again at longer wavelengths, especially in the infrared. No galaxy shines in only one way. Even a calm galaxy contains many stellar ages, many temperatures, and many environments. When SPHEREx measures distant galaxy light in 102 infrared bands, it does not see a simple lamp. It sees a mixed spectral signal shaped by stars, dust, and cosmic expansion. This matters because the history of the universe is, in part, a history of light production. As galaxies form stars, evolve, merge, and enrich their gas with heavier elements, the total amount and character of their emitted light changes. Some epochs contain rapid star formation across many systems. Other periods are calmer. Dust content also changes as galaxies age and recycle material. The sky preserves the combined outcome of these long processes. Every distant galaxy adds a small piece to the total radiance of the universe. A mission like SPHEREx helps estimate how much light galaxies produce as a population, and how that production varies with cosmic time. Ordinary imaging surveys often depend on identifying discrete objects above a brightness threshold. This is useful and powerful, yet it always leaves a remainder. Some galaxies fall below that threshold, some overlap with brighter foreground sources. Some are too diffuse, too redshifted, or too obscured by dust to stand out clearly in standard catalogues. Their individual forms may remain uncertain, but they are not absent from the sky. Their photons still contribute to the observed signal. SPHEREx is well suited to this regime because it surveys the whole sky spectrally, rather than only compiling a narrow list of selected bright targets. It therefore helps bridge the gap between resolved galaxies and the fuller light budget of the cosmos. The light from distant galaxies does not reach Earth unchanged. As it travels through an expanding universe, its wavelengths stretch. A feature that begins in the visible part of the spectrum may arrive in the infrared. A galaxy whose stars once radiate strongly in optical wavelengths can therefore become an infrared source in the observed frame when it's far enough away. This shift is one reason SPHEREx can examine distant galaxy populations through infrared measurements. It is not merely seeing local cool material, it is also intercepting ancient galaxy light that cosmic expansion has moved into longer wavelengths over immense travel times. Because the mission observes in 102 spectral bands, it can do more than record total brightness. It can measure shape across wavelength. That shape carries physical meaning. A spectrum that rises gently toward longer wavelengths can indicate strong dust emission, or an older stellar population viewed at substantial redshift. A sharper change can signal the movement of known galactic features through the observing bands. No single band tells the whole story. The pattern across many bands is what allows astronomers to estimate distance, classify populations, and infer how much of the observed light comes from direct starlight and how much comes from dust-processed radiation. This is especially important for the faint majority. Bright galaxies are valuable, but they do not by themselves describe the full universe. Much of cosmic history is written by systems that are modest in brightness, or too distant to appear dramatic in ordinary images. When many such systems are summed statistically, they can account for a substantial fraction of the background light. SPHEREx can compare the light from known resolved galaxies with the broader diffuse glow that remains after those sources are counted. In this way, it tests whether current galaxy inventories account for the measured radiance of the sky, or whether a meaningful fraction still comes from populations that remain incomplete in catalogues. Observations of distant galaxy light also help astronomers study the balance between unobscured and obscured star formation. Not all starlight escapes directly into intergalactic space. In many galaxies, especially those rich in gas and dust. Some of the light from young stars is intercepted by dust grains. The grains warm and then emit infrared radiation. A galaxy can therefore appear relatively modest in direct shorter wavelength light, while still contributing strongly in the infrared. A full sky mission that measures wide spectral coverage can capture this hidden side of galaxy evolution more effectively than visible light mapping alone. It reveals that part of the universe's luminous history is carried not by exposed stars only, but by reprocessed energy emerging from dusty environments. There is a calm but profound consequence in this. The distant universe is brighter in meaning than in appearance. A small unresolved patch of infrared signal may contain the combined output of many stars in many galaxies across different times. What seems faint in the map can still be rich in information. SPHEREx treats these weak signals seriously. It does not require every contributor to stand clearly alone before its existence is scientifically useful. Instead, it measures collective light carefully enough that whole populations can be studied through their shared imprint. In this region, then, the hidden universe is a census of galactic radiance spread across time. Galaxies near and far release starlight, heat dust, and send spectral signatures through expanding space until they arrive as a layered infrared record on the sky. SPHEREx listens to that record broadly and evenly, drawing meaning from both the bright sources that can be identified directly and the faint unresolved populations that merge into the larger cosmic total. The result is a quieter but deeper portrait of distant galaxies, not merely as isolated islands of light, but as a long collective output that fills the universe with measurable memory. Distant galaxy light does not only tell how much radiance the universe has produced, it also preserves evidence of a specific transition in early cosmic history, when the first strong sources of energetic light begin to alter the state of matter between galaxies. This transition is called ruionization. In the earlier universe, after the first atoms form and long before the intergalactic medium becomes fully transparent to energetic ultraviolet radiation, hydrogen exists largely in a neutral state. Neutral hydrogen is hydrogen whose electron remains bound to its proton. In that state, It is very effective at absorbing certain kinds of high-energy light. Space is not empty during this period. It is filled with diffuse hydrogen gas that acts like a widespread fog, limiting how far the earliest energetic radiation can travel. Rhionization marks the gradual clearing of that condition. As the first generations of stars and galaxies form, they begin producing ultraviolet photons energetic enough to strip electrons from surrounding hydrogen atoms. When this happens, the gas becomes ionized. Ionized gas and neutral gas interact with radiation in different ways. The change does not occur everywhere at once. Instead, early luminous sources carve out growing bubbles of ionized material around themselves. These cleared regions expand, overlap, and slowly transform the wider intergalactic medium. The process is extended and uneven, not a single instant. It proceeds across large ranges of space as many early systems contribute their radiation over time. The lingering record of this era remains visible because light from those distant galaxies still reaches the present universe after travelling for billions of years. Yet what astronomers observe is not a direct moving picture of the fog lifting. It is a set of clues preserved in the spectra, brightness, and statistical distribution of ancient sources. Some spectral features are suppressed when neutral hydrogen is abundant. Others become easier to detect once the surrounding medium is more ionized. The number of visible galaxies at extreme distances, the strength of their emission in particular lines, and the diffuse fluctuations in the background light all help reconstruct the progress of reionization. In this way, the early universe leaves a historical imprint rather than an immediate scene. One important feature in this work is Lyman alpha emission, a spectral signature produced by hydrogen. This line is especially sensitive to neutral hydrogen in and around young galaxies and in the wider intergalactic medium. When the surrounding universe is still rich in neutral hydrogen, Lyman alpha photons are readily scattered or absorbed, making them difficult to observe from very early times. When astronomers do detect this signal from a remote galaxy, it can indicate that the source sits inside a region where the hydrogen fog has already been partly cleared, or that the galaxy itself has unusual power or environment. Recent observations indicate that at least some galaxies are able to create clear ionized regions surprisingly early, though it remains uncertain whether such objects are typical or rare. This is where a mission like SPHEREx enters the story in a distinctive way. It is not designed mainly to isolate a few record-breaking galaxies one by one in the manner of a deeper, narrow-field observatory. Its strength lies in all-sky measurement, spectral coverage, and the statistical power of enormous samples. SPHEREx helps study the epoch of reionization by measuring the accumulated infrared light from faint distant populations and by tracing spatial fluctuations in that light. Fluctuations are small changes in brightness from place to place. They matter because very faint galaxies that cannot be counted individually still follow the large-scale distribution of matter. Their collective glow is not smooth, it carries structure. By measuring that structure, astronomers can infer properties of the populations responsible for it. This approach is important because the sources that drive reionization are thought to include many low-mass galaxies too faint to dominate ordinary catalogues. Observations with the James Webb Space Telescope have strengthened the case that very faint dwarf galaxies likely contribute a major share of the ionizing radiation in the first billion years. Such galaxies may be individually modest, yet they are numerous. Their collective output can outweigh that of rarer brilliant systems. If many of them remain below direct detection thresholds in broad surveys, their presence may still appear in the diffuse extragalactic background and in its clustering pattern. SPHEREx is built to probe exactly this regime, where unresolved populations leave a measurable large-scale signal. The mission, therefore, studies rionization not only through single ancient beacons, but through the total light budget of the early universe. Some surveys identify galaxies and then sum their known contribution. A wide spectral mapping mission can also examine what remains beyond those individually resolved populations. If the diffuse background contains fluctuations stronger than expected from catalogued galaxies alone, it can point to additional faint sources. Models of the epoch of reionization predict a characteristic contribution from early galaxies to the near-infrared background. SPHEREx has the sensitivity and wavelength coverage needed to search for that contribution, and to distinguish it from nearer diffuse components as carefully as possible. There is also a geographical aspect to this old transition. Rionization unfolds in patches. One region around an early galaxy may become ionized while another region farther away remains neutral. The universe during this period is therefore mixed in state and transparency. This patchiness matters because it changes what observers can detect. A remote galaxy inside a large ionized bubble may show escape paths for radiation that would be blocked elsewhere. Another galaxy at a similar age but in a more neutral environment may appear more muted. The early universe is not simply dark and then clear, it is mottled, gradually opening in many locations at different rates. The record, SPHEREx, seeks, is the broad memory of this patchy clearing. It listens for the aggregate signature of early galaxy populations, for the way their clustered light still marks the sky in the infrared, and for the excess background structure that unresolved sources may contribute. In this region of the hidden universe, the subject is no longer galaxies in general, but galaxies as agents of transformation. Their radiation changes the state of cosmic hydrogen. Their abundance shapes how rapidly transparency spreads. Their faint collective light remains measurable long after the process ends. SPHEREx studies that lingering record with a survey wide enough to hold the whole sky, and spectral enough to separate ancient background signals from the many nearer layers laid across them. Within the broad distribution of galaxies, an older pattern remains hidden. The strands and clusters of the cosmic web do not arise from nothing. They grow from tiny unevennesses present in the very young universe, long before galaxies exist, long before stars ignite, and long before hydrogen fog begins to clear. This deeper layer belongs to inflation, the idea that the newborn universe expands with extraordinary speed in a very small fraction of a second. In that brief interval, minute fluctuations in the early cosmic medium are stretched across vast scales. Those fluctuations later guide where matter gathers. The large-scale structure seen by SPHEREx is therefore not only a map of present galaxies, it is also a record of those original ripples, enlarged by cosmic expansion and developed by gravity over billions of years. A fluctuation is a slight difference from place to place. In the early universe, these differences are extremely small. One region holds a little more matter and energy than another holds a little less. At first, these contrasts are tiny, but they matter because gravity acts on them continuously. Over long cosmic time, denser regions attract more material, while less dense regions give up matter to their surroundings. The final result is the structured universe of filaments, clusters, and voids. Without those first irregularities, matter would remain much smoother, and galaxies would have far greater difficulty forming in the pattern now observed. Inflation provides a way to explain how these first irregularities are distributed across the sky and across scale. In the standard picture, microscopic fluctuations in the early universe are stretched outward during the rapid expansion, becoming the seeds of later cosmic structure. This idea has strong support because the universe on large scales is remarkably uniform, yet not perfectly so. It contains just the right level of primordial unevenness to allow structure to grow while preserving broad smoothness. What remains uncertain is the exact physical mechanism behind inflation. Different models can produce slightly different statistical fingerprints in the pattern of the original fluctuations. The structure traced by galaxies offers one way to search for those fingerprints. SPHEREx is designed to help with that search by measuring the three-dimensional distribution of hundreds of millions of galaxies over an enormous cosmic volume. This wide coverage matters because the signatures of inflation are strongest on the largest scales, where the primordial pattern is least altered by the complicated local physics of galaxy formation. Small scales are rich in information, but they are also crowded with later processes such as feedback from stars, gas heating, dust effects, and mergers. The widest scales are quieter in a different sense. They preserve more direct memory of the beginning. A full-sky infrared survey can therefore examine structure in a regime where the early imprint still stands out most cleanly. One of the main targets in this work is primordial non-Gaussianity. This term sounds technical, but the idea is simple enough. If the first fluctuations are distributed in a very regular statistical way, their pattern follows a simple bell-shaped expectation. If they depart from that expectation in subtle but measurable ways, they are called non-Gaussian. That departure matters because different inflation models predict different levels and forms of it. Some of the simplest single-field inflation models predict very little primordial non-Gaussianity. Other models, including some with more than one active field, can produce a larger signal. Observations, therefore, do not merely test whether fluctuations exist. They test how those fluctuations are arranged statistically. The remarkable part is that this ancient statistic can still appear in the galaxy map. It does not survive in a perfectly untouched form, because billions of years of structure growth modify the pattern. Yet on the largest scales, primordial non-Gaussianity can change how strongly galaxies cluster relative to the underlying matter field. In practical terms, it can slightly enhance or reduce the tendency of galaxies to gather on enormous scales. The effect is subtle, and it cannot be seen by eye in a sky image. It emerges through careful statistical analysis of very large data sets. This is why a mission like SPHEREx needs both scale and number. A small survey may be deep, but it does not contain enough of the largest modes of structure. A vast survey contains more of that ancient signal. SPHEREx helps by providing distance information from its infrared spectra, allowing astronomers to place galaxy populations in 3 dimensions rather than on a flat sky alone. Once those positions are measured across a huge fraction of the heavens, the distribution can be analyzed for its large-scale clustering pattern. Astronomers compare the observed pattern with theoretical expectations for different primordial conditions. They ask whether the galaxy field behaves like one seeded by nearly Gaussian fluctuations, or whether it carries the distinctive scale dependence expected from measurable non-Gaussianity. The answer has direct meaning for inflation physics. It can rule out some families of models and strengthen others. This work complements earlier measurements from the cosmic microwave background. The relic radiation from the young universe released when matter and light first decouple. That background already shows the primordial fluctuations in an earlier state. Large-scale galaxy surveys examine the same basic initial pattern after it has had billions of years to grow into structure. These are different views of related information. The microwave background shows the universe when it is still young and largely smooth. Galaxy clustering shows what those seeds become after gravity has amplified them into the web. Agreement between the two strengthens the overall picture. Differences or improved constraints refine it. There is caution in this field, and it is necessary. Galaxy formation is complicated. Observations do not record matter directly, but galaxies, which are biased traces of the deeper mass distribution. Bias in this context means that galaxies do not mark every region of matter with equal fidelity. Different kinds of galaxies occupy environments in different ways. Instrumental systematics, foregrounds, and selection effects can also mimic large-scale patterns if not carefully controlled. Observations indicate that SPHEREx has the survey design needed to constrain primordial non-Gaussianity competitively, yet it remains uncertain exactly how tight the final limits will be until the full mission data are processed and cross-checked. Even so, the basic promise is clear. The hidden universe at this level is not hidden behind dust or distance alone. It is hidden inside statistics. The broad arrangement of galaxies contains information about a phase of cosmic history unimaginably earlier than the galaxies themselves. A map of the present sky becomes, in effect, an instrument for studying the first instance of structure. SPHEREx does not watch inflation happen directly. No mission can return to that moment and observe it in ordinary time. Instead, it reads the surviving imprint in the largest patterns of matter. In this way, the mission uses the current universe as an archive of the very young one, tracing how the tiniest primordial departures from perfect smoothness grow into the grand architecture now stretched across the sky. After the vast scales of primordial structure and the remote light of early galaxies, the hidden universe draws closer without yet entering the Milky Way itself. Around the home galaxy lies a nearby extragalactic sky, populated by neighbouring systems close enough to show broad internal character rather than only distant statistical presence. These galaxies are still far beyond the stars of the Milky Way, yet they belong to a more local cosmic environment. Their disks, dust lanes, stellar populations, and active regions can be mapped with greater continuity than the more remote systems whose light arrives only as faint unresolved contributions. In this region, SPHEREx studies galaxies that are near enough to appear as structured worlds of their own, but still separate enough to remain part of the surrounding external sky. A nearby galaxy is not simply a bright patch on the edge of vision. It is a full stellar system, often containing billions of stars, large reservoirs of gas and dust, and a long history of formation and change. Because these systems are relatively close by cosmic standards, their integrated light can be studied with added richness. Broad regions within them contribute differently across infrared wavelengths. Old stellar populations, warm dust, cooler dust, and regions of recent star formation each leave distinct spectral tendencies. A wide infrared survey across 102 bands can therefore do more than measure the total brightness of a nearby galaxy. It can reveal how different physical components are distributed across its visible extent. The local group provides the most immediate part of this extragalactic setting. It includes the Milky Way, Andromeda, the Triangulum Galaxy, the Large Magellanic Cloud, the Small Magellanic Cloud, and many dwarf companions. SPHEREx does not enter these galaxies physically, but its infrared mapping allows them to be studied as neighbouring islands of matter and light. Andromeda, with its broad disk and extensive stellar content, offers a nearby example of a mature spiral system seen from outside. The Magellanic Clouds present a different environment, rich in irregular structure, active star formation, and dust shaped by gravitational interaction. Each nearby system becomes a laboratory in which large-scale galactic processes can be seen more holistically than in either the far distant universe or the embedded viewpoint from inside the Milky Way. Infrared light is especially useful in these galaxies because it reveals material and populations that visible light alone does not describe completely. Dust can obscure starlight along certain lines of sight, especially in star-forming regions and along dense structural features. In the infrared, that obscuration is reduced, and dust itself can become a measured source of emission or absorption features depending on temperature and composition. This means that a galaxy which looks patchy or partially hidden in visible light can appear more continuous and physically readable in infrared data. The structure does not become simple, but it becomes more transparent to interpretation. Nearby galaxies also allow astronomers to connect large-scale galactic form with the spectral behavior of their internal contents. A spiral arm is not just a visible curve, it is a region where gas density, dust, young stars, and older stellar background interact in a recognizable pattern. A central bulge is not only a bright concentration, it is often dominated by older stars with different infrared colors than the surrounding disk. Regions of intense recent star formation can show stronger signatures from heated dust and molecular material. Even when emission such as SPHEREx does not resolve every small substructure, it can still trace broad contrasts across a neighbouring galaxy and relate those contrasts to physical conditions. This is important because nearby external galaxies provide a comparative view. Seen from within the Milky Way, it is difficult to perceive the home galaxy as a single complete object. Dust, geometry, and internal position complicate that view. Nearby galaxies offer an outside perspective on galactic organization. Their disks, bars, irregular extensions, and tidal distortions can be seen as full patterns. Infrared mapping of these systems helps astronomers compare how galaxies of different masses, shapes, and histories distribute stars and dust. It becomes easier to ask how typical or unusual certain galactic features may be when several neighbouring systems can be studied under the same observing framework. The Large Magellanic Cloud is especially valuable in this respect. It is close enough to display rich structure and active enough to show extensive dusty star-forming regions. Infrared observations reveal how dust clouds, luminous young populations, and diffuse stellar light coexist across a single external system. NASA has already used SPHEREx imagery to show dust-rich features in the Large Magellanic Cloud, illustrating one of the mission's defining strengths. The same galaxy can look very different when measured across many infrared bands than it does in ordinary visible images. Hidden material, temperature contrasts, and broad emission structure begin to separate from one another. A neighbouring galaxy becomes less like a flat smear of light and more like a layered environment. There is also scientific value in the calmer parts of these nearby systems. Not every region is a dramatic starburst or a dense dust complex. Wide stretches of disk light come from older stellar populations whose infrared colours help trace the accumulated history of star formation. Diffuse dust outside the brightest clouds reveals how interstellar material is distributed on galactic scales. Low surface brightness outskirts show where a galaxy thins into its environment. These subtler regions matter because they describe the full galactic body, not only its brightest activity. SPHEREx, as a full sky survey, is well positioned to measure these extended components consistently. Observations of nearby galaxies also support a broader goal of astrophysics. They help connect the resolved and unresolved universe. A close galaxy can be examined as a whole, while still retaining some internal structure. A more distant galaxy may appear mostly as an integrated source. By studying nearby external systems in detail across spectral bands, astronomers learn how combined galactic light arises from stars, dust, and gas. That knowledge can then inform interpretation of far more distant galaxies that cannot be separated internally in the same way. The nearby extragalactic sky becomes a bridge between close complexity and distant simplicity. In this region, then, the hidden universe is found in neighboring galaxies just beyond the Milky Way, where external systems can be studied not merely as points, but as organized infrared landscapes. Their broad stellar bodies, dusty arms, active regions, and faint outskirts all contribute to a richer view of galactic life. SPHEREx reveals these nearby neighbours as spectral structures spread across the sky, close enough to show internal character, and far enough to remain clearly outside the home galaxy. The result is a quieter and more intimate cosmic setting, where the survey begins to trade sheer remoteness for comparative clarity, and where the external universe becomes local without losing its depth. Now the hidden universe turns inward to the Milky Way itself, not yet to its individual stars or to the cold interiors of its clouds, but to the galaxy as a complete environment, from Earth. This home galaxy does not present itself as an object seen from outside. It surrounds the observer from within. Its disk stretches across the sky as the bright band of the Milky Way, while its true spiral form remains concealed by the position from which it is viewed. This is what makes a full-sky infrared survey so valuable. SPHEREx gathers light from every direction in a common spectral system, allowing the Milky Way to be studied as one connected structure. In this region, the focus rests on the galaxy-wide body of the Milky Way, its stellar disk, its central bulge, and the dark dust lanes that divide and soften its visible appearance. The Milky Way is a barred spiral galaxy, which means it has a flattened rotating disk, spiral arms, and an elongated central bar passing through the inner region. At the heart of this larger form lies the bulge, a swollen central concentration of stars. Surrounding it is the disk, which contains much of the galaxy's gas, dust, and ongoing star formation. Seen in visible light from Earth, this arrangement is difficult to read fully. The disk crowds the sky with foreground stars, and dust blocks many lines of sight, especially toward the center. Infrared light changes that view. Longer wavelengths pass through dust more effectively than visible light, and so they recover a broader continuity across the galaxy's plane. The Milky Way begins to appear less as a broken luminous streak and more as a coherent stellar system with large internal zones. This whole galaxy perspective depends on uniform mapping. A single infrared image of one star field says little about the form of the Milky Way as a whole. A complete survey, repeated over the entire sky, allows astronomers to compare one galactic longitude with another and one latitude with another in the same spectral language. Galactic longitude and latitude are coordinate directions centered on the Milky Way's plane and midpoint. These coordinates turn the sky into a grid aligned with the structure of the galaxy itself. When SPHEREx scans this grid in 102 infrared colors, It traces how brightness and spectral shape change from the thin plane to higher latitudes and from outer directions toward the crowded inner sky. The galactic disk dominates much of this picture. It is broad rather than thin in experience, though on cosmic scales it is still a flattened system. Across the disk lie stars of many ages, clouds of gas, regions rich in dust, and the spiral pattern that organizes much of the galaxy's visible matter. From within the disk, this structure appears as a continuous band wrapping around the sky. Its brightness varies from one direction to another because the line of sight sometimes passes through greater stellar density and sometimes through heavier obscuration. Infrared measurements help separate these effects. A bright region can be recognized as a place of strong stellar concentration, or as a place where dust radiates efficiently, or as a mixture of both. The broad body of the disk therefore becomes more physically legible. Toward the center, the Milky Way grows denser and more luminous. The central bulge rises as a thicker and more rounded stellar concentration than the surrounding disk. Visible light images often show this inner region as bright but heavily interrupted by dark lanes, because dust between Earth and the center blocks much of the shorter wavelength light. In the infrared, more of the bulge can be traced through that obscuration. The inner galaxy remains complex, yet the central stellar mass becomes easier to map. This matters because the bulge preserves part of the Milky Way's older history. Its stars tend to represent earlier epochs of galactic formation than many of those in actively star-forming portions of the disk. The bar of the Milky Way also belongs to this whole galaxy view, although it cannot be seen directly in the simple way that an external barred spiral galaxy can be photographed from outside. Its presence is inferred from the distribution and motion of stars and gas in the inner galaxy. Infrared surveys have helped clarify that the central Milky Way is not purely round. It has an elongated inner structure, and that structure helps shape how matter moves through the central regions. SPHEREx contributes to this broad mapping tradition by adding spectral coverage over the full sky, giving further context to the light distribution through the inner disk and bulge. Dust lanes are equally part of the Milky Way's full form. In visible images, they appear as dark rivers cutting through the bright galactic band. They are not empty gaps. They are regions where interstellar dust absorbs and scatters shorter wavelength light, hiding stars behind them. Infrared light reduces this masking effect and also reveals that the dust is itself part of the galaxy's luminous system. The Milky Way is therefore not a galaxy of stars alone. It is a mixed environment in which starlight and dust structure are interwoven on large scales. A full-sky infrared survey can show where the broad obscuring bands lie and how they relate to the larger disk. Seen as a whole, the Milky Way is neither a smooth wheel nor a random clutter of nearby lights. It is an organized galaxy with large components that can be traced across the sky, even from an internal vantage point. The disk provides the extended plane. The bulge thickens the center, the bar elongates the inner mass distribution, and the dust lanes soften and divide the visible pattern while remaining part of the same galactic body. SPHEREx makes this organization clearer because it measures the galaxy across many infrared bands rather than through a single narrow window. The result is a mapped reconstruction from within, assembled patiently from every direction. In this region, the hidden universe becomes the home galaxy understood at its largest internal scale. The Milky Way fills the sky, and for that reason it can be difficult to recognize as one object. SPHEREx helps restore that unity. It surveys the galactic plane, the central bulge, and the surrounding sky in a shared framework of infrared light, showing how the home galaxy extends, thickens, and darkens across the celestial sphere. The Milky Way remains a place of immense detail, yet at this level it stands first as a whole system, structured and far more continuous in infrared light than ordinary vision suggests. Within the broad body of the Milky Way, the next hidden layer is not the dust lane or the molecular cloud, but the stars themselves in their immense variety. A galaxy can look like one continuous band when seen across the sky, yet that band is made from countless individual suns and from overlapping populations that differ in age, mass, temperature, composition, and location. Many of these stars are easy to see as bright points in the night sky, but most belong to crowded and partially obscured populations that ordinary vision cannot sort very well. SPHEREx studies this stellar abundance through infrared light, and in doing so, it helps reveal how different kinds of stars are distributed through the home galaxy. In this region, the hidden universe is the Milky Way's stellar population seen not as a single glow, but as a layered census of many kinds of stars. A stellar population is a group of stars that share broad physical traits or a common history. Some stars are old and cool, some are young and hot, some lie in dense parts of the galactic plane, and some belong to thicker or more extended components of the galaxy. From Earth, all of these populations overlap along the line of sight. A bright nearby star may appear beside a much more distant giant. A crowded region near the plane may mix foreground stars with stars from the bulge, and with stars dimmed by dust between them. The visible sky gives only a limited sense of these differences. Infrared measurement adds another layer of separation, because stars with different temperatures and environments produce different spectral shapes across wavelength. Temperature is one of the clearest stellar properties that affects colour. A hotter star emits proportionally more of its light at shorter wavelengths, while a cooler star shifts more of its output toward longer wavelengths. In visible light, this difference is partly seen as blue or red colour, but infrared data extend the comparison into a regime where cooler stars become easier to recognize and where dust interference is reduced. SPHEREx does not rely only on a single red or blue impression. It observes stars across 102 infrared bands. That broad measurement allows astronomers to reconstruct how a star's light rises and falls across wavelength. This spectral shape becomes a practical guide to temperature, and with supporting data from other surveys, it also helps identify broader stellar classes. Age enters more quietly, but it is present in the population as a whole. Stars do not all form at the same time, and the Milky Way preserves many generations of star formation. Older stars tend to dominate some galactic components, especially the bulge and parts of the thicker disk. Younger stars gather more strongly in the thin disk and in regions where gas and dust remain abundant enough for new stars to form. A single star's age is often difficult to determine directly from colour alone, yet large populations reveal age statistically because stars of different lifetimes and masses evolve in different ways. Giant stars, dwarf stars, and intermediate stages each contribute differently to the infrared light of a stellar field. When SPHEREx measures huge numbers of stars across the sky, it helps astronomers trace these broad population differences from one region of the galaxy to another. Infrared colour is especially helpful for cool stars, which are numerous and often modest in brightness. Red dwarfs, for example, are small and common stars with relatively low surface temperatures. They do not dominate the night sky to the human eye, yet they make up a large fraction of the stellar population of the Milky Way. In infrared surveys, their presence becomes easier to map systematically. Giant stars are another important class. These are evolved stars with expanded outer layers that can shine strongly in infrared light. Because some giants are luminous, they can be seen across large distances inside the galaxy, and therefore serve as useful traces of stellar distribution. A wide spectral census can distinguish many such stars from one another more effectively than a simple brightness map can. Obscuration is equally important in this section because many stellar populations lie behind dust. Obscuration means dimming and reddening caused by material between a source and the observer. Dust absorbs and scatters shorter wavelength light more strongly than longer wavelength light. So a star behind dust may appear fainter and redder than it truly is. In visible light, this can make a hot star resemble a cooler one or hide distant populations almost entirely. Infrared light reduces that confusion. It does not eliminate dust effects, but it passes through dusty regions more effectively and allows many hidden stellar populations to be recovered. SPHEREx can therefore help separate truly cool stars from stars that only appear red because dust lies along the line of sight. This ability matters greatly in the crowded Milky Way. Near the galactic plane, enormous numbers of stars overlap in projection. Toward the bulge, stellar density rises further, while dust complicates nearly every direction. A survey that records stars in a uniform set of infrared bands provides a way to sort that crowd statistically. Some stars show spectra typical of warmer photospheres, meaning they're visible outer layers. Others show the gentler infrared rise associated with cooler surfaces. Some appear strongly altered by interstellar reddening, which is the selective removal of shorter wavelengths by dust. By comparing measured colours across many bands, astronomers can estimate which stars belong to which general populations and where those populations concentrate in the galaxy. SPHEREx is especially powerful here because it observes so many stars under one system. The value is not only in identifying a rare unusual object, though such objects may appear. The deeper value is in building a consistent galactic census. When millions upon millions of stars are measured in the same spectral framework, subtle transitions begin to stand out. The bulge can be compared with the disk. The inner plane can be compared with higher latitudes. Dense fields can be separated statistically into foreground and background components. Infrared colours, used with care and often alongside data from missions such as Gaia, become a way of reading the stellar structure of the Milky Way more coherently than before. There is also a chemical dimension that influences stellar colour indirectly. Astronomers often speak of metallicity, which means the abundance of elements heavier than hydrogen and helium inside a star. Metallicity affects stellar atmospheres and evolution, and therefore affects spectral behaviour. SPHEREx is not a high-resolution stellar chemistry mission in the narrow sense, yet its broad infrared spectra can still contribute to population studies in which temperature, luminosity class, and reddening are disentangled well enough to improve understanding of where older and younger, richer and poorer stellar populations reside. In this region, then, the hidden universe is the Milky Way's immense stellar society revealed through infrared distinction. The galaxy-wide glow resolves into overlapping groups of stars with different temperatures, histories, and degrees of obscuration. SPHEREx does not merely count bright points. It records the spectral character of vast stellar populations across the sky, allowing hidden distributions to emerge from the crowd. The Milky Way becomes less like a single luminous band and more like a layered, humanly unreadable census, made readable at last through measured infrared colour. Between the stars of the Milky Way lies another broad and powerful layer, one that does not shine in the simple way a star does, and does not remain entirely dark either. This is the dust veil of the galaxy. In visible light it appears as interruption, as darkening, as a loss of clarity along the galactic plane. Yet the darkness is not empty space. It is matter spread through the interstellar medium in the form of tiny solid grains mixed with gas. These grains are extremely small, often comparable in size to smoke particles or smaller, but across the great distances of the Milky Way their combined effect is immense. They absorb, scatter, and redden starlight, altering the appearance of the galaxy at large scale. In this region, the hidden universe is the dusty layer of the Milky Way itself, the broad obscuring medium that shapes what can and cannot be seen. Interstellar dust forms from heavier elements created inside stars and released into space through stellar winds and explosive stellar death. Carbon, oxygen, silicon, iron, and other elements condense into microscopic grains under suitable conditions. These grains do not float in isolation. They are mixed with diffuse gas and are carried through the galaxy by turbulent motion, gravity, shock waves, and large-scale galactic circulation. Over time, dust becomes part of clouds, filaments, and broad lanes, especially within the disk of the Milky Way where much of the interstellar material resides. Though each individual grain is tiny, the total surface area of all grains together becomes large enough to interact strongly with light. The effect is most severe at shorter wavelengths. Visible and ultraviolet light are more easily absorbed or scattered by dust than infrared light. This is why the Milky Way's band looks broken and streaked in ordinary images. Dark dust lanes appear to cut across star-rich regions, especially toward the galactic center and along the plane. These lanes are not holes in the galaxy. They're curtains of material between the observer and more distant stars. A bright stellar field can be dimmed until it almost disappears, while a neighboring field with less dust can remain luminous. The visible sky therefore gives an incomplete and sometimes misleading picture of the true distribution of stars. Infrared observation changes this dramatically. Longer wavelengths pass through dusty regions more effectively, which allows SPHEREx to recover light that visible surveys often lose. This does not mean the dust becomes irrelevant. On the contrary, the dust veil remains one of the major physical features of the Milky Way. It still absorbs some infrared radiation, especially at shorter infrared wavelengths, and it also emits its own characteristic signal depending on temperature and composition. What changes is that the veil becomes more readable. Instead of appearing only as darkness, it begins to show structure. Behind it, hidden stellar populations re-emerge. Within it, variations in density and material character become more apparent through their spectral behavior. Dust does more than block light. It also modifies it. When starlight passes through a dusty region, shorter wavelengths are removed more efficiently than longer ones. This process is called reddening. A star seen through dust can appear redder than it truly is because more of its blue light has been scattered or absorbed. In visible surveys, reddening can make interpretation difficult. A distant hot star seen through dust may resemble a cooler star with less obscuration. Infrared data reduce this ambiguity because the light suffers less severe attenuation, and because the spectral coverage provides more information about how the dimming changes with wavelength. SPHEREx can therefore help separate the effects of dust from the intrinsic properties of the stars behind it. Across the Milky Way, the dust veil is not uniform. Some directions show relatively transparent windows through which distant stars and inner galactic structure can be seen more easily. Other directions are heavily obscured, with dense clouds and lanes that strongly suppress visible light. The galactic plane is especially rich in such material because it contains much of the interstellar gas and dust from which stars form, and through which stellar activity recycles matter. The centerward view is often crowded not only because many stars lie there, but because many layers of dust overlap along the same lines of sight. SPHEREx. By surveying all directions in 102 infrared colors, can map these variations across the entire celestial sphere and show how the dust veil thickens, thins, and changes character from place to place. This wide map is important because dust is not merely a nuisance to be removed from observation. It is part of galactic ecology. It helps cool gas clouds, shields molecules from harsh radiation, and provides surfaces on which chemical processes can occur. At the scale of Section 10, those chemical interiors are not yet the focus, but the veil already shows its role as a mediator between radiation and matter. It softens starlight, redistributes energy, and shapes the thermal balance of the interstellar medium. Dust absorbs energy from stars and later irradiates that energy at longer wavelengths. In that sense, the dusty plane of the Milky Way is both screen and source, both obscuring medium and infrared participant. The broad appearance of the galaxy in infrared therefore differs from its visible appearance, not simply because more light gets through, but because a different balance of physical processes becomes prominent. In visible light, stars dominate and dust often appears as absence. In infrared light, dust becomes a structured layer with presence of its own. The galactic plane shows brighter continuity in many obscured directions, and the lanes themselves can be studied as material features rather than only as interruptions. This helps astronomers refine large-scale maps of stellar distribution, estimate how much obscuration affects different regions, and understand how interstellar material is arranged along the disk. SPHEREx contributes to this work through uniformity and spectral range. A full sky survey allows the dust veil to be compared across all galactic longitudes and latitudes with one consistent system. The same instrument measures dense plane fields, higher latitude diffuse regions, inner directions, and outer directions. Because it observes in many bands, it can trace how the effect of dust changes across wavelength, which helps distinguish thick obscuration from lighter reddening and diffuse emission from transmitted starlight. The result is not merely a clearer map behind the dust, but a better map of the dust itself. In this region, then, the hidden universe is the Milky Way's broad obscuring layer, the veil of interstellar dust spread through the galactic disk. What appears dark in visible light proves to be complex matter rather than emptiness. What seems like absence proves to be a structured medium made of microscopic grains with galaxy-scale influence. SPHEREx reveals this veil by looking in infrared light, where hidden stars return and the dusty plane shows more of its true form. The Milky Way becomes not only a galaxy of stellar populations, but a galaxy whose light is filtered, shaped, and partly re-emitted by a pervasive layer of fine cosmic material. Beyond the broad dust veil of the Milky Way, the next inward region is the molecular cloud complex. These are the large cold gatherings of gas and dust from which much of the galaxy's future stellar and planetary material is drawn. They are not yet stars, not yet planets, and not yet the deeply shielded interiors where chemistry becomes most concentrated. At this level, they are extended cloud systems spread across space in knots, ridges, arcs, and broad, dim masses. In visible light, many of them seem like dark interruptions against richer star fields. In infrared light, they begin to show themselves as actual structures, places where matter has collected into cold reservoirs with enough density and enough protection from harsh radiation for molecules to survive in large abundance. A molecular cloud is a cloud in which hydrogen exists mainly in molecular form, meaning two hydrogen atoms bound together as one molecule. Molecular hydrogen is the most abundant ingredient in these regions, but it is not easy to observe directly under the cold conditions common in the cloud. Astronomers therefore often trace the cloud through dust, through other molecules, and through the broader infrared behavior of the region. A cloud complex is not a single neat sphere. It is a large interconnected environment made of many denser and thinner parts. Some regions are relatively diffuse and spread out over long distances. Others gather into more prominent filaments and clumps. Together they form the outer architecture of the stellar nursery. Temperature is one of the defining features here. These clouds are cold by everyday standards, often only a few tens of degrees above absolute zero. That coldness matters because hot gas resists compression more strongly, while colder gas can settle more readily into denser forms under gravity. The cloud does not collapse all at once. It remains supported in part by turbulence, magnetic fields, and internal motion, yet its cold state allows some regions to drift gradually toward greater concentration. At the scale of the cloud complex, the important fact is that the Milky Way contains vast cold reservoirs, where raw material is stored in a form suitable for later structure building. Dust remains mixed throughout this gas, and its role is essential. Dust grains help shield the cloud from energetic starlight that would otherwise break apart delicate molecules. The outer parts of a molecular cloud still feel the influence of surrounding radiation, nearby stars, and the general galactic environment, but deeper layers become progressively safer for molecular survival, because dust absorbs and scatters much of the incoming light. Even at the broad, complex level, this shielding begins to matter. The cloud is not simply a passive pile of material. It is an environment in which radiation, temperature, density, and chemistry all interact, with dust acting as both filter and participant. SPHEREx is well suited to this region because it surveys the Milky Way in 102 infrared colors and measures millions of directions through interstellar clouds. This wide coverage is important for cloud complexes because they are large, extended structures. A narrow observation can reveal one beautiful fragment, but a full-sky spectral survey can trace how cold clouds are distributed across the galaxy and how their broad properties vary from place to place. One cloud may lie near massive young stars and show stronger external heating. Another may remain quieter and more uniformly cold. One may appear as a long filamentary ridge. Another may spread across the sky as an irregular dust-rich complex. Infrared mapping allows these outer cloud forms to be studied consistently. The gas in molecular clouds is not composed of hydrogen alone. Carbon monoxide, water in frozen form on dust grains, carbon dioxide ice, methanol, ammonia, and other compounds can exist under the right conditions. At the scale of Section 11, what matters is not the most protected chemistry hidden in the deepest pockets, but the fact that these cloud complexes are the galaxy's main molecular reservoirs. They contain the ingredients from which later stars and planetary systems emerge. SPHEREx is designed in part to study this material by identifying spectral fingerprints across infrared wavelengths. A spectral fingerprint is a pattern of absorption or emission at particular wavelengths caused by a specific molecule or bond. With enough spectral coverage, broad classes of frozen and molecular material can be mapped across many cloud lines of sight, This gives the cloud complex a new kind of visibility. In visible images, a molecular cloud can look like obscuration only, a dark body standing in front of starlight. In infrared measurements, the same region becomes more informative. Some wavelengths pass through more effectively, revealing stars behind or within the cloud. Other wavelengths show the effect of ice and dust more directly. Variations in color across the cloud begin to separate warmer surfaces from colder zones, thinner material from denser accumulations, and chemically different regions from one another. The cloud is still quiet and dim compared with a field of bright stars, but it is no longer unreadable. Many famous star-forming regions begin at this scale as cloud complexes. Orion, Rho Ophiuchi, Taurus, and the Vela Molecular Ridge are not merely names for beautiful sky objects. They are examples of the Milky Way storing matter in cold, structured form. Some of these regions are closer to Earth and therefore easier to examine in greater detail. Others are more distant and appear as broader integrated fields. SPHEREx contributes by placing them into one spectral framework, allowing comparisons across many environments rather than treating each one as a separate, isolated case. This matters because star formation does not occur under one universal local condition. It unfolds across a range of cloud masses, radiation fields, and structural histories. Cloud complexes are also shaped by motion. The interstellar medium is not still. Shock waves from old supernovae, compression in spiral arms, stellar winds from massive stars, and large-scale galactic flows all influence how gas and dust gather. A cloud complex may grow where material is compressed, stretched where flows shear it, or fragmented where turbulence stirs it. What appears calm in an image is often the slow result of many forces acting over long periods. The structure seen in a cloud today is a temporary state in an ongoing galactic circulation of matter. Even before stars form inside it, the cloud already belongs to the dynamic life of the galaxy. In this region, then, the hidden universe is the molecular cloud complex as a broad cold reservoir. It is the place where gas changes from diffuse interstellar presence into organized molecular structure. It is where dust shielding becomes strong enough for richer material to persist. It is where the future building blocks of stars and planets first gather on large scales. SPHEREx reveals these complexes not as simple dark patches, but as extended infrared environments with measurable spectral character spread across the Milky Way. The galaxy, at this inward step, becomes a place where matter collects, cools, and quietly prepares the raw conditions from which later celestial forms will arise. Inside the broad molecular cloud complex, there are regions where the material grows denser, the radiation field weakens, and the interior begins to separate itself from the more exposed outer layers. These are the shielded cloud interiors. At this depth, the cloud is no longer simply a large cold reservoir spread through the galaxy. It becomes a more protected environment, where external starlight is strongly reduced, and where the physical conditions allow a richer and quieter chemistry to persist. The hidden universe here is not defined by dramatic brightness or obvious shape. It is defined by concealment. Light from outside loses its reach, temperatures fall further, and matter settles into a state that is difficult to observe directly in visible light, but legible in the infrared through the effects it leaves on passing radiation. Shielding means that the dust and gas in the outer parts of the cloud absorb and scatter incoming light so effectively that much less of it reaches the interior. Ultraviolet radiation is especially reduced. This matters because energetic light can break molecular bonds and warm the gas and dust. When that radiation is excluded, the inner cloud becomes calmer in a chemical sense. Molecules that would be fragile in more exposed regions can survive longer. Gas loses heat more effectively. Dust grains remain colder. The cloud interior therefore develops conditions distinct from the outer cloud surface, even though both belong to the same larger structure. A cloud is not one uniform body. It changes inward, layer by layer, as radiation weakens and density rises. The temperatures in these interiors are very low, often only a few degrees above absolute zero. That coldness is not a detail added on top of the environment. It is one of the defining reasons the interior behaves as it does. At low temperature, atoms and molecules move more slowly. Reactions that depend on violent collisions are less common, while processes that involve sticking, freezing, and gradual accumulation on dust-grained surfaces become more important. The gas remains thin by everyday standards, but compared with the diffuse interstellar medium, it is concentrated enough for repeated interactions over long spans of time. The result is a sheltered and slowly evolving chemistry shaped by cold, darkness, and patience. Dust grains are central to this environment. In the shielded interior, they are not only blocking outside light, they are also acting as tiny surfaces on which molecules can gather. When atoms or simple molecules strike a cold grain, they may adhere to it rather than returning immediately to the gas. Over time, thin, icy layers build up around the grains. These icy mantles can contain water, carbon dioxide, carbon monoxide, methanol, ammonia, and other compounds depending on local conditions. The grain surface becomes a meeting place where atoms and molecules can combine more easily than they often do in the gas alone. In this sense, the cold interior of a cloud is not chemically inactive. It is chemically quiet but productive, with much of the important work occurring on microscopic surfaces hidden throughout a vast dark volume. The darkness of the interior is relative rather than absolute. It is not a room with walls, but a region where the outside radiation field has been reduced by many layers of intervening matter. A nearby star behind thick cloud material may contribute very little to the inner environment. The remaining light is faint and filtered. Cosmic rays, which are high-energy particles moving through space, can still penetrate more deeply than ordinary starlight, and can still drive some ionization and chemical change. This means the interior is not perfectly isolated. It remains connected to the broader galaxy through penetrating particles and weak residual radiation. Yet its internal balance is overwhelmingly set by shielding and cold conditions. SPHEREx studies this region indirectly but powerfully. It does not enter the cloud or illuminate it from within. Instead, it measures the infrared signatures imprinted on light passing through or emerging from these dense lines of sight. Molecules and ices absorb infrared radiation at specific wavelengths according to the bonds they contain. Those absorptions leave characteristic dips and shapes in a spectrum. Across 102 spectral bands, SPHEREx can identify broad classes of frozen material and trace where those materials become more abundant. This makes the shielded cloud interior visible not as a bright glowing chamber, but as a spectral environment. Its hidden contents are revealed by what they remove from the light and by how they alter the color of background and embedded sources. Density is another defining property here. The interior is denser than the outer cloud, though still extremely tenuous compared with any ordinary substance on Earth. In astronomy, dense means dense relative to surrounding interstellar space. This increased density helps molecules survive and helps dust grains gather thicker icy coatings. It also means that collisions between particles, while still infrequent in human terms, occur often enough over long spans to support a richer network of chemical pathways. Some parts of the shielded interior are smooth on large scales, while others are filamentary or clumped. The cloud's internal structure is not perfectly uniform, but at the level of this section what matters is the general inward transition from exposed molecular reservoir to protected chemical chamber. As the interior becomes better shielded, the balance between gas and solid material also changes. More molecules freeze onto grains. More of the cloud's chemical inventory shifts into the icy mantles coating those grains. This transfer matters because it changes what remains in the gas and what becomes stored in frozen form. A compound that is rare in the gas phase may still be abundant overall if much of it is locked in ice. SPHEREx is designed to help reveal that hidden inventory. By surveying many millions of lines of sight through the Milky Way, it can build a much broader map of where important ices reside and how common they are in different cloud environments. The dark interiors are therefore not merely obscure places. They are storage regions where a large fraction of interstellar chemistry may reside in frozen silence. These interiors also tend to be acoustically and visually quiet in the imagination, though in physical terms there is still slow motion, magnetic tension, internal turbulence, and gradual redistribution of material. Nothing in the cloud is perfectly still. Gas drifts, density contrasts shift, and pressure and gravity continue their long negotiation. Yet compared with the brighter and more exposed outer galaxy, the dominant impression is one of attenuation. Energy from outside is muffled, temperature is lowered, chemistry is protected. The shielded interior is the Milky Way in a softened state, where raw interstellar matter becomes more secluded and more chemically elaborate at the same time. In this region, then, the hidden universe is the dense protected heart of the molecular cloud, where light weakens, temperatures fall, and chemistry grows richer on cold dust grains. The broad outer cloud gives way to an inward zone of spectral secrecy. Visible light is largely excluded. Molecules endure. Ices accumulate. SPHEREx reveals these interiors through their infrared fingerprints, showing that some of the galaxy's most important chemical preparation occurs not in bright exposed places, but in dark shielded chambers of interstellar matter spread quietly through the Milky Way. Within the shielded interiors of molecular clouds, some regions gather enough mass for gravity to begin overcoming the support of gas pressure, turbulence, and magnetic resistance. Material falls inward. Density rises further. A core forms and contracts until a young star emerges at the center of the collapse. Around that young star, not all matter falls directly into the growing stellar body. Part of it settles into a rotating disk of gas and dust, flattened by angular momentum, which is the tendency of turning material to keep turning as it contracts. In this region, the hidden universe is the newborn stellar system itself, a young star still closely tied to its birth environment and surrounded by the disk from which later structures may arise. The scene is no longer the broad cloud complex or the quiet, protected interior alone. It is the first organized star and disk system forming within that darkness. A young star differs from a mature star not only in age but in condition. It is still gathering mass or has only recently ended the main stage of infall. Its surroundings are often thick with dust and gas. It may remain partly embedded in the cloud that formed it. Its energy output can vary. Its surface and immediate environment are often more active than those of many stable older stars. In visible light, many such objects are difficult to study because dust around them blocks much of the shorter wavelength radiation. In infrared light, they become far more accessible. the surrounding material absorbs stellar energy and re-radiates it at longer wavelengths, so a forming system can stand out strongly in the infrared even when it is faint or concealed in ordinary images. The disk around a young star forms because collapsing cloud material rarely falls straight inward without rotation. Even a slight initial turning motion becomes more significant as the material contracts. Gas and dust spiraling inward therefore spread into a flattened structure around the central forming star. This is called a protoplanetary disk, meaning a disk that can provide the raw material from which planets may later assemble. At this stage, however, the disk is best understood simply as a rotating reservoir. It contains gas, fine dust, and a range of temperatures from warmer inner zones near the star to cooler outer regions farther away. The central star and the disk are not separate stories. They are one connected system shaped by the same collapse. SPHEREx is well suited to this inward region because young stars and their disks have strong infrared signatures. A signature in this sense is a recognizable pattern in the measured light across wavelength. A bare mature star often shows a spectrum close to what is expected from its surface temperature alone. A young star with a disk shows more. Dust around it absorbs energy from the central star and emits additional infrared light, creating excess radiation at longer wavelengths beyond what the stellar surface alone would produce. This infrared excess is one of the clearest indicators that a surrounding disk is present. A survey in 102 infrared bands can detect and characterize such excesses across very large numbers of objects. The environment around a young star is often layered. Closest to the star, material can be relatively warm, especially in the inner disk where stellar heating is stronger. Farther outward, the disk cools. Some systems still retain a diffuse envelope of infalling material around the disk. Others are more exposed, having shed much of that outer cocoon while keeping the disk itself. This creates a sequence of developmental stages, not sharply separated but broadly recognizable. Some young stellar objects are deeply embedded and dominated by surrounding dust emission. Others show the central star more clearly while still carrying a substantial disk. SPHEREx can help sort these stages because the balance of light from star, disk, and envelope changes across infrared wavelengths in a measurable way. This sorting matters because star formation does not end when a central object first appears. The newborn system continues to evolve. Material may still accrete from disk onto star. Jets and winds may carry some matter away along the star's rotational axis or from the disk surface. The surrounding cloud may continue to obscure or feed the system. Dust grains within the disk can begin the long path toward growth through repeated sticking and settling. At the scale of this section, the key fact is that the young system is active and transitional. It is not yet the cleaner planetary architecture of a mature solar system. It is a warm, dusty, rotating environment in the middle of a reorganization. Infrared surveys are especially valuable here because they can find young systems across wide star-forming regions, not only those already famous from detailed observation. A narrow telescope pointed at one nebula can reveal striking local examples, but a full-sky mission can identify large populations of young stars and disks under one uniform observing method. This allows astronomers to compare star-forming regions throughout the Milky Way and ask how common different stages of youth really are. Some clouds may produce many disk-bearing stars still deeply embedded in dusty envelopes. Others may show more evolved systems where the central star is easier to see and the disk is beginning to thin. A consistent infrared census helps map these differences. The disk itself is not merely a decorative ring, it is the controlling structure through which matter moves in the young system. gas orbits, slowly redistributes its angular momentum and drifts inward or outward depending on local processes. Dust grains orbit with it, collide, fragment, stick, and settle toward the disk mid-plane, which is the denser central layer of the disk. Temperature, pressure, radiation, and turbulence vary with distance from the star, so the disk is physically stratified rather than uniform, even when these internal details are not spatially resolved by a survey such as SPHERex. Their existence affects the infrared spectrum of the system. Warm inner dust and cooler outer dust contribute differently, giving the disk a measurable broad shape in wavelength space. Young stars also help illuminate their natal environment. Their radiation heats nearby dust and can carve cavities or bright edges in the surrounding cloud. Groups of forming stars can transform a small region of a cloud from a quiet dark interior into a more structured nursery with mixed temperatures and illumination. Yet many remain partly hidden, especially the younger and more deeply embedded objects. This is why the infrared view is so important. It reveals systems in the act of emergence, when the cloud has not yet released them fully into open galactic space. In this region, then, the hidden universe is the young star and its surrounding disk, born inside the cloud but not yet detached from it. Gravity gathers matter inward. Rotation flattens part of that matter into a disk, and infrared light carries the evidence outward through warm dust emission and spectral excess. SPHEREx measures these forming systems across the Milky Way, turning buried stellar youth into a readable population. The dark interior of the cloud gives way to a more focused hidden structure, where a star begins to shine, a disk begins to organize, and a newborn system takes shape inside the lingering cover of its origin. Around the young stars and within the cold star-forming environments of the Milky Way, a further inward layer appears in the form of cosmic ice. This ice is not arranged as smooth lakes or solid sheets. It exists as thin frozen coatings on dust grains, as cold material within dark cloud interiors, and as part of the raw inventory inside young stellar disks. In this region, the hidden universe is the reservoir of frozen compounds that gathers wherever temperatures remain low enough, and shielding remains strong enough for volatile substances to stay solid on microscopic surfaces. These ices are quiet, faint, and easily overlooked, yet they carry a large fraction of the chemical matter that later enters stars, comets, asteroids, and planets. In astronomy, ice means a frozen volatile compound rather than only frozen water. Water ice is one of the most important members of this group, but it is not alone. Carbon dioxide, carbon monoxide, methanol, ammonia, and other substances can also freeze onto dust grains under suitable conditions. A volatile compound is one that can exist as gas under some conditions, but condenses or freezes when the temperature falls low enough. In the cold reaches of molecular clouds and in the outer parts of young disks, many such materials leave the gas and accumulate in solid form. What appears empty in ordinary images is therefore filled with countless tiny grains carrying frozen mantles built up atom by atom and molecule by molecule. These icy mantles do not form everywhere equally. They require a combination of low temperature, sufficient density, and enough shielding from radiation. If the environment is too warm, the frozen layer does not remain stable, and the compounds return to the gas. If the region is too exposed to energetic starlight, the grains are heated, and the more fragile materials are broken apart or driven off. In the cold, protected parts of star-forming space, however, the balance changes. Dust grains become stable sites where gas phase material freezes and remains. Over time, These grains collect thin but chemically rich layers that represent a major hidden storehouse of interstellar matter. Water ice is especially important because water is abundant and because frozen water helps define the chemistry and thermal character of cold environments. In dark clouds, water often forms on dust-grain surfaces when oxygen-bearing species encounter hydrogen under cold conditions. Once present as ice, it helps create a stable matrix in which other compounds can be mixed. Carbon dioxide and methanol can also become abundant in these frozen mantles. The result is not a pure crystal of one substance, but often a mixed coating with internal complexity. At the level of this section, what matters most is the existence of the reservoir itself. The Milky Way hides enormous amounts of frozen matter on microscopic grains spread through large volumes of space. SPHEREx is designed in part to study exactly this hidden reservoir. Its infrared observations can detect the presence of ices because frozen compounds affect light passing through them at characteristic wavelengths. The mission surveys millions of lines of sight in the Milky Way, making it possible to trace where water ice and other major frozen compounds appear across star-forming environments. This is a profound change in scale. Earlier missions and targeted studies reveal individual regions in detail, but SPHEREx can provide a broad census. It can show how widespread these ices are, how they vary from cloud to cloud, and how strongly they appear in different environments from dark interstellar cores to the disks around young stars. This wide census matters because cosmic ice is part of the material history of planetary systems. Before planets exist, before rocky surfaces form, and before atmospheres become stable, some of the relevant ingredients are already stored in these frozen mantles. The disk around a young star inherits material from the parent cloud, including dust grains that carry ice. In the colder outer regions of the disk, much of that frozen material can survive for long periods. It may later become incorporated into larger bodies such as comets and icy planetesimals, which are small early building blocks of planets. Even where later heating changes or removes some of the ice, the earlier frozen reservoir helps determine what material is available and where it is available during the formation process. There is an important spatial contrast here. Close to a young star, temperatures are usually too high for many volatile compounds to remain frozen. Farther away, the same compounds can exist as ice. This creates broad thermal zones inside disks and clouds, regions where frozen material is stable and regions where it is not. A reservoir is therefore not just a list of substances, it is a map of where those substances can remain stored in solid form. SPHEREx helps reveal that map statistically across many systems. It does not need to resolve every grain or every small disk structure directly. It reads the large population through spectral signatures spread across the sky. The presence of ice also changes the physical behavior of dust grains. A grain with a frozen mantle is not the same as a bare mineral surface. The icy layer can make sticking during gentle collisions more likely, which matters for the first stages of grain growth. It can also trap volatile molecules that would otherwise remain mobile in the gas. This means that the cosmic ice reservoir is not only passive storage, it influences how solids behave, how chemistry is preserved, and how matter is partitioned between gas and solid phases in star-forming environments. The hidden universe at this level becomes a frozen economy of materials, with large consequences for later evolution. Observations indicate that these icy reservoirs are common in the cold, denser parts of molecular clouds and in young circumstellar disks. Yet their exact abundance and variation from region to region remain incompletely mapped. This is one of the reasons SPHEREx is so valuable. A mission with full-sky infrared coverage can move beyond a few famous clouds and construct a broader Milky Way view of frozen chemistry. It can compare quiet clouds with more active star-forming regions. It can compare more deeply embedded systems with somewhat more exposed disks. It can ask where water ice is especially strong, where carbon-bearing ices are more prominent, and how the total frozen inventory shifts across environments. The quietness of these reservoirs should not hide their importance. They are among the main ways the universe stores fragile compounds during the earliest phases of star and planet formation. Much of the future material history of a planetary system may pass through this frozen stage. Water that later enters a comet, an asteroid, a planetary mantle, or an atmosphere can spend an earlier chapter as an ice mantle on a dust grain in a dark cloud or a cold disk. Carbon-bearing molecules that later participate in more complex chemistry can also begin in these reservoirs. The ices are small in scale and broad in consequence. In this region, then, the hidden universe is the frozen inventory of star-forming space, spread across dust grains in clouds and disks throughout the Milky Way. Water ice and other volatiles gather where cold and shielding allow them to remain solid. These reservoirs preserve matter, reshape dust behavior, and carry essential ingredients forward into the era of planet building. SPHEREx reveals them on a galactic scale through infrared measurement, showing that some of the most important material in the story of stars and planets spends a long quiet interval not in fire or gas, but in frost. At the deepest inward level of this survey lies not a cloud, not a disk, and not even the ice reservoir as a whole, but the structure hidden within the frozen material itself. Cosmic ice is important because its molecules contain bonds, and those bonds interact with infrared light in precise ways. A chemical bond is the connection between atoms within a molecule. When infrared radiation passes through icy material, certain wavelengths are absorbed because the bonds in the molecules vibrate in response to that light. Each kind of bond vibrates at characteristic energies, and so each frozen compound leaves a distinctive pattern in the spectrum. In this final inward region, the hidden universe is the bond-level structure within interstellar and circumstellar ice, where chemistry becomes readable through the smallest repeating motions of matter. This is what makes infrared astronomy so powerful for cold chemistry. Ordinary visible light may show that a cloud is dark or that a disk is dusty, but it does not easily reveal which molecules are frozen onto the grains. Infrared light can do more because molecular bonds respond directly to it. A water molecule, for example, contains oxygen-hydrogen bonds, and those bonds absorb infrared light at specific wavelengths. Carbon dioxide contains carbon-oxygen bonds with its own distinct pattern. Methanol, ammonia, and other compounds also imprint the light in recognizable ways. The result is a spectral fingerprint, meaning a characteristic pattern of absorption that identifies a material through its interaction with light, rather than through direct visual appearance. In the frozen mantles coating cosmic dust grains, these fingerprints are often broad rather than narrow because the molecules are not floating freely in a simple gas. They are locked within solids, mixed with neighbouring compounds, chilled to low temperature, and influenced by the local physical environment. The exact shape of an absorption feature can therefore reveal more than the mere presence of one molecule. It can suggest whether the ice is relatively pure or mixed, whether the grains are warmer or colder, and whether radiation has altered the material. A bond does not only announce that a substance exists, it carries information about the condition of that substance within the ice. Water ice is one of the clearest examples. In many cold clouds and disks, it forms a major part of the frozen mantle. Its oxygen-hydrogen bonds produce strong infrared absorptions that make the presence of water measurable even when the ice itself remains invisible in ordinary images. Carbon dioxide ice and carbon monoxide ice can also be identified through their bond signatures, and these species often appear in different relative abundances depending on environment. Methanol is especially interesting because it points to active surface chemistry on cold grains. Its presence suggests that simple carbon-bearing material has undergone additional reactions in the frozen state. Ammonia and related compounds add further evidence that nitrogen as well as oxygen and carbon participates in this chemistry. SPHEREx is built to measure these bond-driven fingerprints across an immense number of lines of sight in the Milky Way. This does not mean it acts like a laboratory instrument examining one grain at a time. It observes the integrated effect of many grains along a path through a cloud or around a young star, and it does so with enough spectral coverage to identify the major absorption features of important ices. Because the survey is all sky, the resulting chemistry map is not confined to a few famous targets. It extends across different environments, from dark molecular clouds to embedded star-forming regions to disks around young stars. The bond signatures therefore become part of a galactic census. This census matters because chemical storage in ice is not uniform. In some places water dominates strongly. In others, carbon-bearing ices make a larger relative contribution. Some lines of sight indicate fresh cold mantles with little processing. Others suggest that radiation, heating, or repeated cycles of freezing and thawing have altered the material. The bonds preserve this history in subtle form. When infrared light encounters a molecule in ice, the precise depth and shape of the absorption reflect not only molecular identity, but also the physical setting of the bond. A bond in a mixed ice matrix can behave somewhat differently from the same bond in a purer frozen environment. In this way, the chemistry of interstellar frost is not merely a list of ingredients. It is a record of local conditions written into molecular vibrations. There is elegance here. The universe at this scale is read through motion too small to see. Atoms connected in a molecule stretch, bend, rock, or twist when light of the right wavelength arrives. These motions happen at microscopic scale, yet when they are repeated by vast numbers of molecules on vast numbers of grains, they become detectable across interstellar distances. A dark cloud or a young stellar disk thus communicates its chemistry through the combined choreography of countless molecular bonds. Bond-level information also helps link astronomy with planetary origins. The compounds identified in interstellar and circumstellar ice are not abstract inventory items. They are the materials from which later chemical environments inherit part of their composition. Water, simple organics, carbon-bearing volatiles, and nitrogen-bearing compounds can all pass through this frozen stage before some fraction becomes incorporated into larger solid bodies. By measuring which bonds are present and where, SPHEREx helps clarify what raw chemical mixture is available in different star-forming settings. It does not determine the final composition of a planet directly, but it reveals the earlier frozen chemistry from which later paths begin. Observations indicate that many of the key ice features SPHEREx targets are widespread across dense Milky Way environments. Yet the full galactic distribution and environmental variation remain incompletely known. This is why a mission with 102 infrared bands and full sky coverage is so significant. It can move chemical knowledge beyond scattered case studies and into a broader comparative framework. It can show where certain bond signatures are common, where they weaken, and where mixtures change across cloud depth and disk environment. the galaxy becomes chemically mappable, not only at the level of gas and dust, but at the level of frozen molecular structure. In this region, then, the hidden universe reaches its most intimate scale. At this final level, matter is read through infrared absorption by vibrating molecular connections on cold grains. SPHEREx reveals that some of the most important hidden structure in the universe is not large, bright, or easily pictured. It lies within frozen compounds and within the bond patterns that allow chemistry to announce itself across the darkness of space. The hidden universe revealed by SPHEREx settles at last into a calm and unified picture. What begins as the whole sky in infrared light gradually narrows through diffuse background glow. The great web of galaxies, the distant history of cosmic light, the early clearing of intergalactic hydrogen, and the statistical memory of inflation itself. It then draws closer through neighbouring galaxies, the full body of the Milky Way, its immense stellar populations, its dust veil, its molecular clouds, their shielded interiors, the birthplaces of young stars and disks, the cold reservoirs of cosmic ice, and finally the molecular bonds within that frost. At every scale, the same lesson remains. Much of reality does not hide because it is absent. It hides because ordinary sight is too narrow to read it. SPHEREx changes that condition with patience rather than spectacle. It does not depend on a few dramatic targets alone. It surveys broadly, evenly, and repeatedly. It lets faint things matter. It lets structure emerge from comparison. It lets chemistry appear through absorption, and lets distant history appear through background light and large-scale patterns. The universe it reveals is not separate from the visible one. It is the same universe seen more fully, with dust no longer serving only as darkness, with clouds no longer serving only as silhouettes, and with hidden cold material taking its place beside stars and galaxies as part of the same continuous cosmic order. In that wider view, the sky becomes less empty and more layered. The Milky Way becomes less like a band of light and more like a living system of stars, dust, gas, frost, and formation. The distant universe becomes less like a scattering of unreachable lights and more like a preserved record of long development. Infrared colour makes this continuity legible. SPHEREx gathers it quietly, one band at a time, until the hidden universe becomes something that can finally be read with steadiness and care.